In this video, we will look at a second optimization problem. So let's jump right in. Here we have a box with no top is to be built by taking a 6-inch by 10-inch sheet of cardboard, cutting X inch squares out of each corner and folding up the sides. Find the value of X that maximizes the volume of the box. So let's think about what's happening. So we have this piece of cardboard. It is 6 by 10. We're going to cut out these squares from each corner. Those squares are X by X. We're doing that at every single corner. And then we're going to fold along these dotted lines that I'm drawing, right? So we're folding up those edges to create this box. The box has no top. We are told it has no top. And what do we want to do with this box? Well, we want to maximize the volume. So what is the volume of a box? Well, it is going to be length times width times height. So the length of this box is going to come from not the entire 10, because we are getting rid of, we're folding up some of those edges. So what is the length of that box? That length is going to be 10 minus, well, you're going to subtract this x over here. Also, you're subtracting this x over here. So 10 minus 2x. That is the length of our box. What is the height? The width of our box. Well, the width is going to come from here. So it's not this whole length of 6. It's going to be 6 minus 2x. That will be our width. And what is the height? Well, the height is going to be just that value x itself. So that is the volume that we are looking to optimize. Solving this, multiplying it out, we have a volume of 60x minus 12x squared minus 20x squared plus 4x cubed, which is 60x minus 32. This was a 12x squared minus 32x squared plus 4x cubed. So that is our volume. What are we going to do with that volume? Well, we want to take our derivative. So v prime, our derivative is 60 minus 64x plus 12x squared. What are we going to do with that derivative? Well, with that derivative, we want to set it equal to 0. We're going to find critical numbers. When we go about finding these critical numbers, we could use the quadratic formula. X is equal to negative b, so we'll have positive 64 plus or minus square root of b squared minus 4ac. Oh, I have my ac backwards because I did not write it as 12x squared. Not that it would have mattered, because I was multiplying them, and multiplication is associative, but I'll switch it around. Or commutative. I mean, it's also associative, but it's commutative. All over 2a. It would have mattered here. And if we do that, we get 64 plus and minus the square root of 1216 over 24. And if I were to round these two solutions, we'll get 4.12 and 1.21. So we get two different solutions here. Do both of these solutions make sense? So what is the feasible domain of this function? What x values make sense? Well, our values of x, they should be at least 0, right? So they should be larger than 0. Otherwise, we wouldn't be folding anything up. And since this length is 6 and we're cutting out 2 corners, we should not cut out a corner of length 3. So 3 should really be the maximum. Once we go past 3, it's no longer going to make sense over here. So our value of x should be between 0 and 3. So this 4.12 won't make sense. And let's do a sign chart. For the derivative of our volume, we'll go from 0 to 1.21, and then go from 1.21 up to 3. So if you plug 1 into this right here, you're going to have 72 minus 64, which is a positive number. If you plug in 2 into that same thing, you're going to have 108 minus 128, and that will be a negative number. So right here, so we're increasing to decreasing, so right there at 1.21, we must be at a maximum. That's what we're trying to do. We're trying to find the maximum volume. And so we have a maximum when x is equal to 1.21 inches. When that happens, our value so we're just finding the value of x. If we wanted to know all of the dimensions, we have it's 1.21 inches by, let's see, 6 minus 2 times that. So 6 minus 1.42, minus 2.42 is, so I did not write this down to the side, 3.58. And the 10 minus 2.42 would be 7.58. So the dimensions of the box would be here. We were only asked to come up with the value of x. So what size do we square are we cutting out from those corners? And that is a second optimization problem. Come back for our next video. We will look at yet another optimization problem. We will see you there.